folks. We raise our glasses and we toast the train with a choo-choo.
Choo-choo!
One last thing, don't forget to tip your bartenders, and we will begin with our first speaker. First speaker is Afi Khan. He is a colleague of mine at U of A, fellow graduate student, and he'll be talking about India's first solar space observatory. Afi, the floor is yours.
Woo-woo!
This is Afi reading for Shakespeare, reading for the character Hamlet. To be or not to be, that is the question.
Afi, it's not the auditions yet.
It's not the audition.
No,
but I
ne-
memorized my lines.
That's next week.
What do I do now?
You signed up for this. You got to talk up there.
Oh, okay. But I memorized my lines.
Hey, next week maybe, but this.
My clicker doesn't work.
That's my fault. Try it now.
I can go back to Shakespeare.
Do it now. Point it at here. Point it at here.
No, still doesn't. Oh, now it does. So where were we? To be? No, sorry. I'm Afa Khan. I'm a third-year graduate student at the University of Arizona, and I'm doing a PhD in astrophysics. But before I chose this life where I don't get paid enough to do a lot of work, I was working on a space mission back in India, and I helped build India's first solar space observatory, and I'm going to tell you all about it. It's called Aditya L1. It was launched on 2nd September 2023, not 24. Typo. It was my sister's birthday, and she was like, "What are you giving me for birthday?" I said, "Well, a 2,000 kilogram satellite that's going up there. Happy birthday." Well, she was not impressed. She's not an astronomer, of course. It is now located 1.5 million kilometers from Earth, well beyond the orbit of the moon, and this is the first time India was able to insert a spacecraft into what is called an L1 orbit, which is sort of a balance point between the sun and Earth, and that's because we want to look at the sun forever and send our data to the Earth forever. And I'll talk a little bit more about it as we go along. I have to get used to this. So in terms of what science Aditya wants to do, I'll go into the details of this, but the main science objective is to do science that other NASA and ESA space missions have not done. So fill in a gap that humanity has in its knowledge about the sun. And you might be wondering, well, what do we don't know about the sun? It's a star nearby. We should know everything about it by now. Uncle Galileo saw it 400 years ago, and by now we should know everything. The answer is that we don't. And some of the things that we want to understand is how this corona around the sun, which is its atmosphere, is heated, how the energy is transmitted, how do these massive what so-called coronal mass ejection that you hear a lot about on Fox News every time one happens, and then how does the dynamics of the solar atmosphere couple with what is happening inside the sun, and finally to understand that distribution of that wind and its impact on satellites around the Earth. And that's probably one of the most important reasons, because all of our lives are dependent on these multi-billion, trillion-dollar investment in space, and one solar eruption can actually knock it out. So do we have something that can do a surveillance for us 24/7 and tell us a flare is coming? So this is what happened on the 2nd September. PSLV launched this 2,000 kilogram satellite into orbit, and then for the next 3 months, almost next 3 months, it was just on a journey to the orbit where it would remain, hopefully, for a very long time. The mission's baseline design is to last for about 5 years, but potentially a mission like this can last for 20 years. Example is SOHO at L1, which was launched several decades ago and is still functional, still sends back data. So basically it did a few loops of the Earth, increasing its orbit gradually by doing orbital burns, and then did one transfer maneuver to get into this very Lesser-just-like orbit where it kind of loops around L1, and the size of this loop is about, ask me later, I forgot. Just like I forgot my Shakespeare lines. But it's quite a significant loop, so it doesn't go and sit at a point, but still is orbiting. But if you ask me what, it's orbiting nothing. It's basically being swing like a rope. If you are two people and you spin a rope, and the rope makes a kind of figure, that's the figure that this is making. And the gravity of the Earth and the Sun combination keeps it in orbit, and it has fuel on it that burns and keeps the spacecraft in that orbit by periodically correcting its attitude. And this is how the spacecraft looks like. And these are this spacecraft has multiple scientific instruments because, well, if you're going there, making a spacecraft and spending 10 years building it, you should not put all your eggs in one basket. So there are multiple instruments. Well, there's a scientific reason for that as well, which is that we want to comprehensively cover different parts of the electromagnetic spectrum and also particle energy spectrum. And I'll talk a little bit more about that. But we want to cover these different regimes of scientific observations, and that's why multiple instruments make a lot of sense. And they are sort of independent of each other, so if even one dies, you have other instruments that can still accomplish part of your scientific mission. So we have a visible emission line coronagraph, VELC, the solar ultraviolet imaging telescope, the star of the show tonight. That's the telescope I helped build. I shouldn't be humble. I designed it. I went up. I was the lead of the system till it went to CDR, and then somebody else built it for me. PAPA, which is a particle counter, SOLEX, Aspects are both particle counters. There is an in situ magnetometer that measures the magnetic field at L1. So these instruments combined give us a lot of, sorry, I'm gonna go back, yes. A lot of information about the instrument. So the primary payload is VELC, which kind of sits on top of the spacecraft. This is a coronagraph. It basically blocks the disk of the sun and tries to look at the faint gas around the sun in the visible line. That's why the name visible emission line coronagraph. And it will look like something like the eclipse. So it creates an eclipse in orbit, trying to observe this gas around the sun. And it's critical because there are a few things we don't understand about the sun. One of them is the surface of the sun is around 6,000 Kelvin, but the gas surrounding it is about 2 million Kelvin. And that's called the solar corona, solar atmosphere. There are different terms for it. And we have a gap in our understanding of how this hotter thing is on the outside and it is being fed by this cooler thing on the inside. That does not make sense from the laws of thermodynamics. But when you throw in magnetic field and you throw in complicated gas dynamics, you can make sense of it. But we don't have enough information to solve that mystery. And this is the closest star to us. So kind of weird that we haven't figured that out yet. Then we have, oops, yeah, so that's VLC. Trying to go to the next payload. And that's SUIT. Right next to it, it's a smaller imager. It looks at the sun in the ultraviolet, and by imager, it's basically taking pictures, beautiful pictures, but in the ultraviolet wavelength, between 200 to 400 nanometer.
Oh, is that it?
And
Did you find it?
It's unique because
Yeah, that's it.
although there have been many solar missions that have
Thank you. Can you
taken
please
images of the
blast
sun
it?
in the full disk, both from the ground and in space, but this 200 to 400 nanometer wavelength has not been covered. And that's because this wavelength is pretty notorious for a lot of reasons, and I can go into those if you are interested. But it's very challenging to build a telescope in that wavelength because the detectors are not good enough, the coatings are bad, and so developing those detector and coating technology took us so much time that somebody could only build an instrument like that in a decade from now. So this is SUIT. It looks small, but it's actually almost a meter in the optical in the length. The optical bench is about a meter in length, and this is the aperture door. The door opens, and inside it is just a 2-meter telescope and a detector. And then we have a bunch of filters that basically help us select the wavelength that we are interested in observing. Now, before I go into the details of what SUIT does, because if I do that, then I'll do injustice to this audience. I need to give you a little bit of a background. So we live with this star. We live with this one star. We can now, with our technology, look at its surface, from Galileo, who looked at the sunspots 400 years ago, to now making videos like this. So this is not Soot or from Aditya, because Aditya is still in its commissioning phase. This is from another similar observatory that went in an orbit around the Earth called the Solar Dynamic Observatory, and observed the sun in a further ultraviolet wavelength at around 304 angstrom. And you can see that there is a lot of dynamic activity going on here, and this is sped up. The sun spins around its orbit in about 15 to 30 days, depending on whether you are at the equator or the pole. But you can see a lot of dynamic activity. And the scientists are curious about how this happens. But before that, I have a curiosity for you, and this is a trivia question. So audience, how much time does light take from traveling from the sun to the earth?
Raise your hand.
Hey, raise your hands. Disqualified. This first time space drafter. Disqualified. I've done 2 of these talks. Just no humble brag. You heard the answer. Come on. There at the back. Gentlemen. No, you have your hand raised. Yeah, sorry. 8 minutes. And why so? Oh, because they have traffic police writing speed tickets. Oh, they have Einstein police who said that, well, light can't travel faster than 300 kilometers per second, and so the sun is about 150 million kilometers. Do the math. I can't. I'm an astrophysicist. I use a computer to do the math. Come on. Trivia question number 2, because I'm feeling generous.
It's not charging. Why is it not
Today,
I can't figure it out.
well, my clicker is not feeling generous to me today.
Oh, that's my fault.
No problem.
There you go. Do it now.
After the technical
Ah.
difficulty.
No. No?
No. Trying? Oh, no. Wait. Trivia question
Yeah.
number 2. How much time does the light take to travel from sun's core to us? The person who got the answer right, do you want to take another guess? Still 8 minutes? Are you an astrophysicist?
Not
Did you-
thousands.
No?
Yeah, more
Okay.
than thousands.
You're keeping up with your, well, thousands of years in the ballpark. Somebody has a better estimate? I'm deliberately ignoring the astronomer. I know you. I know you. You get paid enough to buy those. No, I'm kidding. You don't. Actually, yes. Himansh, please go ahead. This was not a setup. What is the answer? Gets an F in stars. He can't pass his comprehensive
Yeah, it's
exam.
not 10,000.
Anybody else?
I know.
Anybody else? At the back. I wouldn't give it to you. You're close. You want to take another guess? It's 11 million. No. It takes 2 million, so nobody gets it. It's about 2 million years, and that's because the photons that are generated inside the sun because of fusion of hydrogen bounce around a lot because it's very, very dense inside. So before they can come out, they bounce around a lot, and it takes a lot of time for them to come all the way to the top. But I'm feeling very generous today, but my clicker is still not. Is it just me, or is it the clicker? Double or nothing.
No, it should work.
Lady at the back, double or nothing for you. Because you got 10,000 years, it's a long time. How much time does it take for the solar wind particles to reach Earth? Himansh, do you want to pass your stars exam? Anybody? No? Nobody? Guess, come on.
Jeez.
Something else is going on. 4 days. It takes 4 days for solar wind particles to wind is fast, but not as fast as the light. Unfortunately, nobody gets double or nothing, but prize for person at the back over there, for sure. Okay, moving on. So we know this one star very well, the sun, because we can look at its surface. We can make these telescopes and look at its surface. If I remember correctly, there's now like 10-meter telescope just to observe the surface of the sun. We send rockets, we send balloons, we send these spacecrafts to study the sun because we care about it. But then that's probably it. That's the only real data point we have if you want to understand a star up close and personal. Other stars are almost like point sources, so we don't get a lot of information about them. Of course, people devise clever tricks to understand the stars, and some other day I'll talk about that. But Sun is unique. It's the closest star to us. It allows us to understand its surface, its dynamics, its properties, the magnetic field, all of this complex phenomena. Let us make models for how other stars would be, and there's a huge diversity of stars. So one star doesn't reveal secret of all stars, but it gives us some clues, and that's why we do this.
That's your problem.
So a little overview of the sun before we dive into the instrument. It has a core in the center where hydrogen is meeting hydrogen, colliding with it and creating helium, and the process, the total mass of the hydrogen that combines together to form the helium is slightly less than the mass of the helium, and that mass disappears, goes into energy according to Einstein, and that energy is the photons that are emitted. And then after bouncing around a lot within the core, they go through this radiative zone where the transfer is mostly photon traversing, then into a convection zone. You can imagine it as a region where the plasma is boiling and stirring up, just like boiling water, rises up, gets up to the surface, cools down, and circulates back. And in the end, there is photosphere, and that's where the plasma becomes thin enough for the photon to just free stream in one direction, and streams in every direction, and that's the light that reaches us in 8.3 minutes from that surface. But that's not it. The sun has an atmosphere, because not only is it a ball of gas, but it's a ball of ionized gas, and it generates magnetic field just like a magnet. And that magnetic field then traps the plasma, and there's a saying in solar physics which says, well, the magnetic field tells plasma what to do, and the plasma tells the magnetic field how to be. So they are like in this whole conundrum of to be or not to be. Oh, damn it, I'm going back to, no, I'm regressing. Damn it. The me in the alternate timeline was an actor. But anyway, so the corona is this hot ball of gas that is being ejected from the sun, because sometimes these magnetic field lines that are on the sun get twisted up and they trap a lot of energy, but at some point they have to break apart. And that breakage releases not only the energy but also the charged particles that are trapped in the magnetic field, and resulting in a surrounding of the sun that is also ionized. And that is what we call as the solar corona. We understand a lot about it. We know that the photosphere is at 5,000 Kelvin. If you go a few hundred miles above that, the temperature kind of remains stable or drops because there is this hot plasma around it. But then at about 1,000 kilometers above the surface, the temperature shoots up, 10,000 Kelvin, 20,000 Kelvin. Any takers? 20,001? No. 30,000 Kelvin. 50,000 Kelvin. Any takers? No. 60,000 Kelvin. 1,000,000 Kelvin. 2,000,000 Kelvin. In a height difference of about 100 kilometers, 200 kilometers, barely the thickness of our atmosphere of this tiny little planet we call Earth, the temperature goes from a few thousand kelvins to 1,000,000 Kelvin. And we don't know why. We haven't completely understood this phenomenon. For a planet, for a star that is right next to us, for all the satellites we've sent to understand it, we haven't really solved this problem. So there is this mystery. If we don't understand our own star, how do we understand, quoting Carl Sagan, trillions and trillions of stars that are out there? So this is an important mystery to solve. Apart from that, sun is also not like a stable thing. Over the year, or an 11-year cycle, it goes through what is called as a solar cycle. And you might hear in the news, the sun is at the maximum of its solar cycle, and there's a threat to the satellites because it's erupting. And basically what happens during the solar cycle is the magnetic field activity on the sun quietens down. There are fewer magnetic loops forming and twisting and breaking and erupting, to a point after a few years where there are a lot of sunspots, there are a lot of these twisted magnetic field lines that are exploding, they're creating this phenomena called flares, prominences, and then it goes back to silent mode. Do all stars do that? Do all stars show this variability? What happens to this variability in the ultraviolet? What happens to it in the visible? These are some of the questions that we try to answer about the sun. Living with this big ball of gas. Still struggling with this flicker. I'm not sure why.
It should be working. There you go.
So, why do we care? I mean, the scientists care because they're like, we want to understand the parameters of the magnetic hydrodynamic simulation so that we can simulate the stars. Never mind. It's related to directly to life on Earth. The auroras are a result of the solar activity. We see this beautiful show in the sky, the ripples in the glows are connected to what is happening on the sun, because these charged particles are hurtled towards everywhere in space, come towards Earth, get trapped in a magnetic field, and then hit the atmosphere and creating these ripples and glows. A few 100 years ago, just this beautiful light show. But a few billion years ago, if Earth did not have a magnetic field, the solar wind from the sun would have ripped off our atmosphere, would not have created a situation that could sustain life, because all the life on the planet would have been polymerized or destroyed by this hard ultraviolet radiation, hard particle distribution, and we would be a barren planet. Today, we care more because your cell phone, the street lights, everything around us is connected to this network of satellites that we have put around. And these charged particle storms can be strong enough that they can knock them out. We already know that they're strong enough that they can also affect infrastructure on Earth. A few decades ago, a nuclear reactor was shut down because of solar magnetic activity, because the power grid yielded. So a strong flare from the sun directed directly towards Earth could disrupt life on Earth. So we care in the modern world about this. I was trying to scare you about this ultraviolet radiation and the magnetic field. Well, the magnetic field is not the only thing that saves us. We also have an ozone layer, which is basically created by the sun and destroyed by the sun. But the balance of this ozone's existence protects us from getting any ultraviolet light down to the surface. The sun is emitting broadly across the spectrum. It emits X-rays, soft X-rays, near ultraviolet, far ultraviolet, and radiation at all different sorts of energy. Only the visible light filters down on Earth, and in fact, we are the ones who have adopted to the light that filters down. Our life is dependent on that, and our eyes adapted over the period of evolution to look at that visible radiation. So if somebody asks you, why do you see only visible light, you can blame the sun. But this picture just shows you that all sorts of radiation is coming down. A lot of it doesn't make down to Earth and is absorbed at different layers of the atmosphere. The ultraviolet specifically is responsible for formation of ozone and destruction of ozone. So it maintains this nice balance of ozone. So if the sun there are activities on the sun that starts making more of this ultraviolet radiation, what happens? The ozone will deplete, and we will get fried by this harmful UV radiation which we have not adapted to. What if it goes down? Similar consequences, the ozone cycle would get disrupted. But more than that, this radiation also deposits energy in different layers of the atmosphere. So if this energy balance, the sun varies over time, then so can the climate of the Earth. And in fact, we have strong evidence that in the past, major solar events have definitely led to large variability in Earth's climate. And that was one part of the climate change debate, that can you prove that this is because of carbon dioxide and not because the sun is varying? And the scientists raised their hands. Well, we don't know because we haven't observed the sun enough, so we need to send some space mission to observe the sun and tell you whether it's the case or not. But if you're a climate change skeptic, I must tell you, we've spent billions of dollars trying to say, well, the sun is the culprit, we can keep running our gas cars and not worry about it, can't blame it all on the sun. That's not the case. We know to very high accuracy that solar variability is not responsible for the current anthropogenic climate change. So something very interesting. It took many years of research to do this. Let's come back to Soot now. I think I've given you enough background on Sun-Earth connection and how Sun operates to tell you more about Soot. So Soot operates in this band where both the wavelengths where the ozone formation happens and the ozone dissociation happens at a lower level in the atmosphere. So it's trying to understand the sun at the wavelengths, which is key to our existence. Apart from that, it has several scientific objectives that are directly related to understanding the sun better, and directly or indirectly helps us understand, connects it to our existence. So coupling and energetics of the solar atmosphere, as I said, we don't understand how energy transfers from the photosphere all the way to the corona. We're trying to understand that. Dynamics of the solar atmosphere. How do these eruptive events happen? Like, why does it suddenly explode? How much energy is there in an explosion? How many of the large explosions that can knock out our satellites can happen over 100 years or in the next 10 years, just like we worry about asteroids hitting the Earth? Prominence study. These are basically these loops of magnetic field that stay in forever, for a very long time, and don't erupt, and suddenly one day choose to explode and throw out this huge mass of plasma towards anything that is in its way, and we don't understand it very well. So we want to understand the mechanisms responsible for that, how these coronal mass ejections initiate very early, and then how does that affect the space weather, whether it's the assets around the Earth or the astronauts on their way to Mars, or even colonies on the moon. And sun climate studies. How does short-term and long-term variability of the sun in the ultraviolet affect the global climate, and what role does it play in affecting different climate cycles? And that is an important question to answer. How relevant is sun? So how do we do that? So Soot is a very simple instrument. It's a camera, takes an image of the full disk of the sun at a very high resolution so that you can resolve very small features on the surface, at the same time look at this giant disk of the sun. So sun is about a degree in the sky. Please correct me if I'm wrong. About a degree? Half a degree? Half a degree.
Yes.
Half a degree in the sky. And when you talk to astronomers, some of us make these small fields of view which are like a few tens of arcsecond. The people who are looking at planets, they are like trying to be sub-arcsecond, and they don't care about anything outside, so they can make instruments for that. But then to make an instrument that covers an entire very large field on the sky, at the same time maintain a very high resolution, is very challenging, specifically in the ultraviolet. So again, let me remind you, this is the full emission from the sun. So all of that is emission from the sun at different wavelength. The peak of the thing doesn't matter much, but if you add all this up, that comes to be about 1400 watts per centimeter squared, just above the surface of the Earth. We are looking at this wavelength region where there is like a lot of difference from the brightest part to the smallest part, several factors. And we have these filters, which I don't want you to memorize for the test, but maybe I'll ask them anyway. That happens a lot in grad school. But we have these filters, and their role is to isolate different lines. And what do these lines do is basically they look for emissions from different hot ions that are tracer for different activities or different temperatures of the gas. So in the end, what we're trying to do is we have these different ions at different wavelength, and they exist at different temperatures, and at different altitudes from the surface of the sun. So we want to create an onion peel 3D image of the sun where we can connect different features across the layers and say, oh, this particular emission goes like this, but at this altitude it dies out, or it takes a turn, and the magnetic field, the plasma is following the magnetic field, so that's the behavior of the magnetic field. And from there we could derive probably the magnetic field is somehow taking the energy, breaking up in the higher atmosphere and depositing energy into the corona. One of the hypotheses. And there are several different hypotheses to kind of try and explain why the corona is super hot, for instance. That's one of the science objectives that it tries to address. Now before I move on, oh, where did it go? A geography lesson. Yes, so SUIT is an instrument that was built at what is called as the Inter-University Center for Astronomy and Astrophysics. It's one of the premier national labs, government-funded national labs in India, which purely does astronomy and astrophysics. And this is our beautiful campus where we have a bust of Newton, not sitting under an apple tree, but a banyan tree, because that's India. So no apple falls on his head, but probably a monkey throws one at his head. And then we have Galileo, and we have Aryabhatta, and we have Einstein, who's just looking up, pretending that it was not him who threw the apple. And this is where my office was, right in front of two banyan trees that also the architecture represents two Roche lobes, two stars that are really close to each other, and they are exchanging matter in close proximity. So the architect was one of India's finest architect, Charles Correa, and he thought through about the astronomy theme and kind of created the architecture. Just so that you're not lost, I'll give you a quick geography lesson. This is where I was in India. The city is called Pune. This is Bangalore. This is where the big space agency's headquarters is, and this is Sriharikota, where the rocket was launched. So the rocket was launched. You saw the launch, and the first light happened a few weeks ago in January, and this is the first light image of the disk of the sun. In one of the filters, the list I showed you is the magnesium 2 filter that traces the temperature of the corona, and you can see all these features in there that are being looked at. SUIT is going to do these large images every minute, and it's also going to look at a smaller region on the sun every 4 seconds for next 5 years in 11 filters. That means we'll be generating 20 gigabytes of data every day for the next 5 years at least. And by the rumors that I've heard, we have enough fuel, if nothing else goes wrong, to last for a decade, maybe more. So a lot of data, so a lot of jobs for the grad student. The first light happened because that door opened. That was the biggest worry I had when I was designing this system with a team of 70 engineers. The guys who are making the door, you need to have your A game on. And they did. The door opened, it's a multi-deployment door, it closed back, it opened again, and it can do that 1,000 times so that we can move our instrument, look at the sun, look at other targets, and go on. And then, not only did we look at one of the wavelengths, we looked at all these different wavelengths that I showed you, and we have nice, interesting results coming out already. These images still are not super interesting because these are just calibration images. But in the end, we want to create these. So as I said, there are these smaller regions we look at. We want to look at these interesting regions where there is a bright event happening. So SUIT not only looks at pre-assigned regions, but if a solar flare happens and the scientists are sleeping, it would automatically lock onto a solar flare and observe it till the solar flare goes away. That kind of onboard intelligence is quite challenging to implement. Trust me, I know. If this video is not playing, could you play? And this is the first dynamic, I think it should, I don't know. It does. This is the first dynamic event, a prominence caught by SUIT, already only in its performance verification phase in the first month of operation. We can see these interesting dynamic event that happens. There are two reasons why it doesn't look as brilliant as the Solar Dynamic Observatory. One is the wavelength. At that wavelength, things are more fuzzy. Second is, still, instrument is not completely calibrated. This is how the satellite looks. It's 2-meter sized satellite sitting on this launch vehicle fairing, ready to be integrated. This is the integration facility, a few human beings for scale. That's the launch vehicle, the PSLV. Still one of the cheapest way to get into space. And that's just the night before we launched. Thank you very much. Yes. Question, I only have time for one because I also did the little theatrics for you. Gotta keep science interesting, otherwise you'll not get funding. Ask JPL. Savage! I'm savage! They'll never give me a job. Question.
Are you able to talk to the solar radiation levels involved in the orbital area and the potential impact on the electronics and what's done to mitigate that?
That's a good question. So I'm not an expert at that, but the other...
Repeat the question.
Yes, the question was, can we measure the impact on the electronics? Can we measure the impact in situ, right?
And what's done to mitigate it?
What's done to mitigate the radiation?
Right, lead shielding, or how you
Yes.
getting away from it?
We're significantly far. There are missions that have gone closer, but all the hardware is specially designed electronics that are radiation hardened.
Radiation hardened. Okay.
For a very for surviving 20-year mission life. That was my requirement. I want to have electronics and systems and mechanisms.
It's very expensive.
Ask me about it. $200,000 analog to digital converter. This small, real estate. It was in my hand, and I was like, can I run away with it? And then I was like, no, maybe not. So that's the answer. We had specialized electronics to survive that environment, and ISRO has been doing this for a very long time. We have geostationary satellites that do communications for us. 10 years, lifetimes, they already have experience to do such a thing. But that's the answer. Thank you so much.
Alrighty, thank you, Afi. Oh, yeah, I'll take that. Thank you. Alright, so checking the time, it is 8:08, so let's call it 15 minutes for intermission. We will be back here at 8:25. See you then, and come over and check out our merch table. We got some freebies. and Jackie are coming on up. Listen, it's been a long night. Danny and Jackie, 2 postdocs here at the University of Arizona. Tell us what's going on in the news in the last month.
Thank you. I'm Danny, and this is what
The Astronomy Comedy Hour.
well, she's the Astronomy Comedy Hour, because not me, because we're gonna start a little somber tonight as we pay tribute to some fallen brethren, the little copter that could, the Martian helicopter Ingenuity, which unfortunately lost its ability to fly last month. Yes, maybe moment of silence for Ingenuity.
Ingenuity.
Okay, that's enough. So what is Ingenuity? So Ingenuity is a helicopter that hitched a ride with the what? Well, no, it still is. It's not. It's like a little dead. It's not fully dead. You know, the Monty Python joke. So Ingenuity hitched a ride to Mars with the 2020 Perseverance rover. And when it reached Mars, it became the first aircraft to achieve controlled flight on another body than the Earth, which is pretty impressive. And it really was quite impressive. So Ingenuity was really just meant to be kind of a tech demo, just let's show off what we can do. But it really outdid itself during the time that it was on the Martian surface. It performed 72 flights instead of its planned 5 flights. It lasted for 3 years once it reached Mars, even though its initial mission was only meant to be about a month. And it traversed about 14 times more distance across the Martian surface than had been planned. So it really went above and beyond, a bit of an overachiever. And it really did deliver as this tech demo. I mean, it successfully flew in Mars's very thin atmosphere. This is not like sending Dragonfly to Titan, where you basically just like go like this and you're flying on Titan. This is pretty impressive. It really proved some skeptics wrong. It was impressively resilient. It was not built to last through the Martian winter, but it managed to successfully. And it really helped out its buddy Perseverance, the rover, by kind of scouting and looking across the Martian surface to see what's going on. So what happened to our little friend? Well, when it was coming down from its 72nd flight on January 18th, it had some navigational issues. It lost contact with Perseverance, which it stays in communication with. And then what happened is while it was landing, it damaged at least one, if not more, of its rotor blades, meaning that it could no longer take off. What they think might have happened is that it was at a particularly featureless and dull part of the Martian surface, and its navigational sensors couldn't quite figure out what was going on. Out of respect, I won't make any Mars jokes about how boring it is. But that being said, it isn't quite dead. It can't fly, but it's not fully dead, but it can't fly anymore. So it is being retired. And so while this is pretty sad news, I think it's safe to say that Ingenuity really raised the bar for itself, proving skeptics wrong and helping pave the way for more exploration of Mars in the future.
Okay, now we're going to go really far away, way out of our solar system, and learn about a hungry black hole. So we love a sensational headline, and Nature Astronomy did not disappoint this week with the publication of a paper titled "Monster Black Hole Powers the Brightest Known Object in the Entire Universe." Actually, nope, that was the press release headline. You got me. Less sensational is its proper title, "The Accretion of a Solar Mass Per Day of a 17 million solar mass black hole." So that's That's not fun, so let's break it down. Okay, so space dress regulars will know that I wake up mumbling these next couple of sentences constantly because this is one of my passions. A quasar shines so bright it often outshines all of the starlight in an entire galaxy, and the supermassive black holes residing inside of them often reach 1 billion times the mass of the sun or even more. Okay, so the name quasar comes from its original name as a quasi-stellar object. It's so small and so bright on the sky that it looks like a star, but its spectrum instead reveals these peculiar non-stellar features. So that's how we know that it's not a star in our sky. So in the images on the screen, you can see that this very bright point source over here, it looks like a star. But in the spectrum that comes from the Very Large Telescope, a real place in a very long country called Chile, reveals the signatures of metals and hydrogen gas that can only be from an accreting quasar. So the quasar in question has a record-breaking intrinsic brightness of 500 trillion times the brightness of the sun, and resides so far away that it took 12 billion years for its light to reach Earth. So in astronomer terms, about redshift 4. Using information from the spectrum, astronomers can determine the accretion rate of the supermassive black hole, or how fast it's consuming matter and getting larger. So a typical value of this might be a few tens times the mass of the sun per year, but this study found a whopping accretion rate of 1 sun per every day, making it the fastest accreting object in the entire universe. So you might be wondering how we missed such an object, since searches for quasars remain an active area of research and are the sole reason that I get paid. But this thing was so bright that it was immediately discounted as a star, and that's because they were using a machine learning classification with the Gaia star survey, and they were basically like star, not star, star, not star, and they were like, star. And so no one looked at it until they were like, let's put a spectrum on it, and they found out, oh, look, you get a press release out of this. So since this object wants to obliterate every record in the universe, let's also consider the size of the accretion disk, or the ring of heated matter that is actively interacting with the black hole. It is 17 billion solar masses of black hole inside an accretion disk that is 9 full light years across. This is the largest accretion disk ever discovered. They are typically light weeks across. This is not the end of what we will get to learn about such a crazy object in the universe. It will likely be a target for the Gravity Plus project, which is an upgrade to the Very Large Telescope Interferometer, designed to accurately measure the mass of black holes. In the future, it will be easier to find and classify objects once the European Space Agency's new 39 meter telescope is on sky. Is that right? Okay, really? Okay, in the Chilean Atacama Desert. If this was discovered on the Very Large Telescope, do people here have any guesses for what ESO's next big telescope is called? You can shout it out. It is indeed the Extremely Large Telescope. The end.
Just, do you want to pronounce this word? Jimt? Jumt? Okay, thank you. Okay, yeah, so kind of in time for Oscar season, astronomy and science is not immune to a good press campaign, and so we now bring you news of the Barbenheimer star. Yes, very exciting. You might be wondering, what could that possibly mean? Like some sort of like pink star in a black hole? That would maybe even somehow make more sense, but that's not the case. We'll get to it, but kind of think just, you're mixing up some things that kind of don't go together, and then there's a big explosion, which I guess kind of explains Barbenheimer. So what is going on? So a group of researchers observed a red giant star called J0931 plus 0038. So you can see why we might want to come up with a name like the Barbenheimer star, rather than those letters and numbers. And what they did is they found that it had a very peculiar chemical composition. The amounts of different elements it had of different atomic weights just made kind of very little sense. And so that star, J blah blah blah, is not the Barbenheimer star, but it got its peculiar composition from the Barbenheimer star. So what does that mean? So stars form from gas in the interstellar medium, and that is enriched, or that material comes from previous generations of stars. So the composition of a star is somewhat indicative of the material that it was formed with, and thus its kind of parent stars. And so this is something called stellar archaeology, right? Because you kind of piece together what went on in the past, piece together our galactic history by looking at kind of different, data and things you can find today, which I think is probably one of the better brandings in astronomy. So this J blah 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 star's weird composition tells us that its progenitor, the Barbenheimer star, or part of its parent, must have also been quite weird. So it existed in the very early universe, in maybe the first 500 million years after yes, I think that's right, after the Big Bang. It must have had its own very peculiar composition, and it was also very massive, like 50 to 80 times the mass of the sun, and that its death is kind of inexplicable. Given its mass, it should not have gone supernova, it should have just collapsed into a black hole, but it must have gone supernova if it was spitting its material out for other stars to form from, and so there really is no single model of stellar death or element creation that can explain this. So I think that might be why it's called the Barbenheimer star. There was a big explosion and you're mixing things up that don't make sense. Now I will say this is a very cool result. I might have some question about the branding of this Barbenheimer star, but I mean, branding works. Here we are talking about it. So yeah, it's a pretty cool thing we can do by looking at one weird star and learning about another weird star, and that tells us more about how we came to our place in the universe.
Okay, welcome to Doofus, our final story of the night. Here at Space Drafts, Dr. Krolikowski and I have made very clear our disdain for doofuses, or dumb or overly forced astronomical acronyms. We also hate coordinates for names. The rise of AI-assisted help in coming up with catchy titles cannot be blamed entirely, because everything I'm about to show you has been, well, as far as I know, came up with by brilliant PhD astronomers. So your taxes pay NASA, and NASA pays us to come up with stupid names for the work we do. So today we thought we'd highlight some of the most egregious names, but with the educational bonus of telling you what they're about. Okay, first, we have an instrument. The Florida Multi-Object Imaging Near-Infrared Grism Observational Spectrometer, or FLAMINGOs. The F, L, and A are all in Florida. This instrument is designed, it's not so bad.
Sure.
Choo-choo, also. Okay, this instrument is designed for infrared observations of the center of the Milky Way and star-forming regions, capable of both imaging and spectroscopy.
Wait. Where's the O?
Observational.
Sure.
Yeah. Okay, so next, this is a good one. We have the pervasive overview of companions of every M dwarf in our neighborhood, Pokemon. The K stands for companions. This is a study meant to study cold M dwarfs in the Milky Way, which are stars that might host exoplanets, but exoplanets could be a false positive in the face of a stellar companion. These are being observed with the WIN and the Lowell Space, it's not a space telescope, the Lowell Observatory, here in Arizona. That's cool. Okay, Pokemon. A particularly egregious one involves skipping over words entirely, which is the all-weather Muse supernova integral field nearby galaxy, or amusing, where weather, field, and any sensible connecting words are omitted. To my knowledge, it's not actually even studying supernovae, but instead the galaxies that host them, so that makes sense. A fun one is the FRB line of sight ionization measurement from light cone AA omega mapping, flim-flam.
I like that one.
Which offensively includes another acronym, FRB, or fast radio bursts. These are actually simulations meant to demonstrate a redshift survey that could be performed by finding fast radio bursts in distant galaxies. Speaking of ones that contain acronyms, we have the worst one of the bunch, the ALMA Manga Quenching and Star Formation Project, or ALMA Quest. You may have heard me talk about ALMA, the Atacama Large Millimeter Array. It's my favorite telescope. Guess what? ALMA doesn't stand for ALMA. The A stands for ALMA. I'm assuming it is meant to study nearby galaxies and how they shut off formation of stars, but I was so angry at this one that I didn't even read the paper. And finally, one that should not have even passed the drawing board, and I am certain was a ChatGPT project, is the Cosmological Hydrodynamical Simulation of Structure, Formation, and Feedback Physics in Galaxy Evolution, or Crocodile. This is a hydrodynamical simulation meant to demonstrate how galaxies form and evolve when they're subject to black holes, supernovae, and other extreme physics. So, For a sticker, I want one of you to stand up and defend one of these and tell me why you think it's acceptable. If no one stands up, you get no sticker. So you have like 10 seconds. See? They get no defense at all. Oh, there's a defender. What? You're so right. I'm the only funny one. Okay, thank you. Thank you for attending. We will have our second talk now. Goodbye.
I like flim flam.
I do not like flim flam. No, I do like flim flam.
You don't like flim
No, I do. I
Alrighty.
changed my mind.
Thank you, Jackie and Danny, for telling us about the highs and lows of the last month in astronomy. That brings us to our second and final talk of the night. I am very pleased to introduce Manisha Shrestha. She is a postdoc at the University of Arizona, and she'll be telling us about energetic explosions in the universe. Manisha, come on up.
Give me like a minute. Why is it not showing up? Give me a minute. Why is it not showing up? I'm very confused. Give me more than a minute. I don't know what's happening. I'm very confused. Come on. Do it. Okay, we're almost there.
Okay.
Almost there, almost there. Woo! Okay. One more minute. Okay. I'm ready.
Great.
Do it.
Okay. I'm not very funny and I don't have any theatrics, so it's hard to follow all those talks, but I will talk about something that is pretty, I think, it's very exciting.
Oh no!
So I'm a postdoctoral researcher and I work on a lot of things that goes, let's wait.
Choo-choo!
Shall I just...
Oh, it's the Amtrak on time. Okay. I think you're good.
Perfect.
I think you're good.
It's an Amtrak as well, so there are people. So I work on things that explodes in sky, and these are very, very exciting. And I will be talking about one particular kind of explosion called gamma ray bursts. Previously, Genevieve in a spacecraft gave an amazing talk about another kind of explosion called supernova, but today I'm not talking about that. Here is just a beautiful picture of a gamma ray burst, but it is an artistic rendition. We cannot take this kind of image in sky, but I just love how colorful and beautiful this image is. So, okay, you have heard a lot about stars by now. So I want to start with stellar evolution or life cycle of stars. Just like us, stars goes through different phases of life. And it is determined by, you can see there are two different directions it goes through. And this is determined by how heavy the star that formed is. If I could. Okay. So you heard all about the sun. So if the star is as massive as the sun or less than 8 solar mass, then this is the evolutionary track, which I really don't care about. I care about these kind of stars actually, which are at least more than 8 times the mass of the sun. So these are very, very massive stars I'm talking about. And the reason I start from here is so that you kind of get an idea about the different things I will say later on. So these stars basically at the very beginning is fusing hydrogen in the center, and that is producing the energy just like the sun is doing right now. And it keeps fusing that. Once it is out of hydrogen, it starts to fuse other elements. And at the very end, when it is iron fusing time, it actually, the iron takes energy to fuse rather than producing the energy. So that causes imbalance in the star, and then you have this explosion, which is called supernova. And I said I won't talk about supernova, but I'm talking about it here very quickly. And this supernova actually ends its life either as a neutron star, very dense, small star, but very heavy, or as a black hole. So this is just to give you an idea. Now let's get back to gamma ray bursts. I will take you back a bit of history. So many of you might know, around 1960, do you know what was a very major thing happening in the world? Cold War was going on. So US and USSR at the time were keeping an eye on each other and trying to see if any of the country were creating nuclear weapons. And in order to check if another country was creating nuclear weapons, they were keeping an eye on one particular kind of signal, that is gamma rays. So these are, if you look at the light and look it as a wave, gamma rays are this extremely energetic part of the electromagnetic wave or the light. Now, in order to look at that, US launched satellite called Vela satellite, and this was keeping eye on if there were any kind of nuclear test was happening. Now, in 1967, they detected this burst of gamma rays, which was very energetic, and at first they were worried, but very soon they figured out it wasn't actually coming from the Earth or even from the moon, but it was coming from somewhere else. And that was very exciting, but also it was very difficult question in astrophysics, and people were not sure where it was coming from. But not just that, just the analysis of the data, like we complain about analyzing our data and not understanding it. But at that point, it took them more than 8 years to analyze the data and have any kind of semblance of what was going on. So once it was detected, this was a very big deal in astrophysics at that point. It was very mysterious, very energetic, and it kind of had a lot of implications, and we didn't understand what was happening. To give you an idea how interesting it was for astrophysics community, in 1995, there was this great debate, which was about the distance scale to gamma ray bursts. Like, how far are these objects? So there was this debate. Around 75 years before this, in 1920, there was another great debate, if you know. It was about the distance scale of the universe. So after 75 years, we had this debate about how far these gamma ray bursts are. And there were two, obviously, for debate. One was talking about if it was within our galaxy or if it was coming from somewhere far away from galaxy. Now here in this, what you have is these all dots are all the gamma ray bursts that were detected by this mission called BATS, which was launched around 1971, that was looking at these gamma rays. And what you can see here actually is that dots are coming from all over the sky, right? There is no preferential direction. And so Bond thought it must be coming from faraway galaxies, because if it was coming from our own galaxy, then you would expect it around this area, right? Like your galaxy is here, we are in the galaxy, so if you're looking through it, then it should be all coming from one direction. However, Lamb thought that it could be that this neutron star that was forming from the explosion of massive stars, it could be ejected in different parts of the galaxy, and still you could get this kind of distribution, and it could be coming from there. Now, another big reason for this was that these bursts were so energetic that it was hard to explain if it was coming from outside of our galaxy. When I say these are so energetic, what I mean is that in these few seconds, the amount of energy it creates is actually greater than the total amount of energy our sun creates during its billions of lifetimes. So it is very, very energetic. And if it is coming from faraway galaxies, then it has big implications. 2 years after that debate, it was kind of settled. So this very, very sad-looking GRB was observed in 97. So with the theme of having very bad acronyms and name, we are also not very good at naming anything. So the way we name our GRBs are basically we say GRB, gamma ray burst, because it is a gamma ray burst. And then we just name the year, month, and the day. So in 97, we detected this GRB. And interestingly, we were able to figure out what was the host of this GRB was, looking at the spectral features. From that, we found that it was at around redshift of 0.8, so which is around few billion light years away. So that, in context of how big our Milky Way is, which is around 500,000 light years, we figured out that these were coming from pretty far away galaxies. Now, once we started learning more and more, we were getting more and more data points. What you're looking at here is basically how many GRBs, all the GRBs we are seeing. So in y-axis is number of GRBs. And in x-axis, it is called something called T90. Basically what it means is for how long this gamma ray burst lasts for. And you can see that when we collect this data, it actually separates into two different populations, and it is divided by this 2-second line. So if it lasts less than 2 seconds, then obviously we call them short duration bursts. So again, we are not good at naming things. And if it is longer than 2 seconds, obviously we call them long duration bursts. So these are the two main kind of gamma ray bursts. Now, even though their name are very not so fun, their origin or how they are formed is really exciting. So for short duration gamma ray bursts, this wasn't supposed to happen. Okay, for short duration gamma ray burst, we think it is coming from merger of the neutron stars that was formed from supernova. So when you have two neutron stars, it starts to collide together, and then this collision can create this jet-like ejecta that can create this short duration burst. So this was theorized. In 2017, for the first time, we actually detected this merger of neutron star, and we saw short duration gamma ray bursts as well. Could you play this video? I don't think I can.
Is it not playing?
No. If you just click there, if you go back and click again, it should work.
There it goes.
Perfect. Here is just how this works. It is just like an animation of how neutron star merger would look like. So you can see there is some ripples coming out, and then there is some very energetic emission coming off. This is the jet, and if we are looking through that jet, that's how we detect gamma ray burst. Now, you saw that it created ripples, and it is called it's called gravitational waves. And I'm very nice, and I made my question much easier. So I said that in 2017, for the first time, we saw the merger of neutron star. My question for you is, when was the first time we detected gravitational wave? Okay, I see some hand raised there. Yeah, go ahead. Okay, perfect. So yeah, it was I said it was easy. I was just trying to be nice. So it was coming from the merger of two black holes, and in 2015, LIGO Virgo detected this merger of black hole and got the gravitational wave detection. So for the long gamma ray burst, we think it is coming actually from explosion of very massive stars. So where I'm talking more than 30 solar mass or something like that. And again, there is supernova. But what is the difference from supernova here is that these objects also have this jet-like structure in addition to this explosion. So what we think is happening is this very massive star is rotating very fast, which launches the jet along with a supernova explosion happening. So two different things are happening. And if we are lucky enough to see through this, then that is when we detect the gamma ray burst. And after a week or so, we actually can see the supernova signature, and that is kind of what I do and what I'm interested in. Now, I said all of this very interesting thing, and you might be asking, why do we care about these objects? But also at the same time, maybe you're not asking that because you are here in the evening, so you might enjoy these kind of talks. But I wanted to give a little bit of context why we care. So the first thing is, these are very interesting places where we think these very heavy elements like gold, platinum are formed. Just to give you a brief kind of summary, you know, during the Big Bang, we have the hydrogen, a bit of helium and lithium formation, right? After that, all the higher elements like carbon that we are made of are formed in this center of these massive stars. That's why Carl Sagan said we are made of star stuff, right? But once we go to these higher elements like gold, we really didn't know where it was formed because it cannot form in the center of massive stars, and we didn't think it could form when the supernova happened. And one of the main places that this could happen was this extreme environments like gamma ray bursts. And in 2017, that GW170817, that was the first time we actually saw signature of these heavy elements from any astronomical sources. Another very exciting thing is now we are entering an era where we can do astronomy in slightly different way than we have been doing. So in astrophysics, right, most of the time what we are doing is we are collecting the light from an astronomical source, we are analyzing that and getting information about these astronomical sources. But now we are entering in an era where we are actually getting two different kind of information about the same object. So here from the new binary neutron star merger, we are also getting these ripples called gravitational wave, and we are also getting the electromagnetic emission in the form of gamma ray bursts. So we can actually study about two different things in a very distinct way that was not possible before. So this is very exciting time, and we call it multi-messenger astrophysics. So this is like bread and butter for us right now. So this is what we work on. Another thing it is that it can map out distant universe. When I say these are very energetic, they act like a lighthouse, right? Like this beam of energy coming from very far away galaxies. So far away, a lot of the long duration gamma ray bursts, the median kind of redshift is 2.8. I always think in redshift, so it will take me some time to tell you how much it is in billion light years, but it is around 11 billion light years. I just learned for this talk. One of the farthest one we have ever detected is around 13.1 billion light years away, and if that number means something, it is very close to the edge of the observable universe. So these objects are coming from far away, very energetic, so they can act as a beacon of light, and we can actually use it to study the properties of this very far away galaxy. And here as an example, this was a very energetic gamma ray burst which was used to actually study the properties of our own Milky Way galaxy. Actually, the light came through the Milky Way band, and we were actually able to study the property of the dust in our own Milky Way. Now, towards the very end of my talk, I want to talk about this brightest gamma ray burst of all time. So it happened in October of 2022, and this is a Hubble image. So this is how it looks like. We don't see the jet or anything. So this bright spot is the GRB, and this extended is where the host galaxy, where this burst happened. And this was so bright, like so bright, I cannot explain. It was really interesting. So we think this is like 1 in 10,000 year kind of event. So maybe in next 10,000 years, we might see something like this. But just to give you an idea, like for the energy it created, these were the previous brightest GRB we had. And then this is the 221009A, or we call it BOAT, the brightest of all time. So this was very energetic, and also it happened very close by. So it was around redshift of 0.151, which is around 2 billion light years. So this is like a backyard for us who works in long gamma ray bursts. So it was so close by, it was so bright, we were excited, everyone was following up, and we being in Arizona, we obviously needed to follow it up. So we used most of the telescope we have access to, and we pointed towards this GRB. We wanted to understand, at least our group was most interested about understanding what kind of star must have exploded to create this much energetic GRB. And we were looking for supernova signatures and all these things. Unfortunately, we don't see clear sign of any supernova signature. And this GRB created a lot more question actually than answer. So we thought there was something bright so close by, it should answer a lot of the open question we had in GRB physics, but it proved us wrong. Now we have even more question, which is good thing that we can get more observational time and funding now, but it was very, very interesting object. And it got a lot of press, so if you are interested about reading about this GRB, you can search it, and there are a lot of information about this GRB out there. So I will end my talk by saying, I have been asked this many times, so these are beautiful objects, very interesting. Don't worry, it won't kill us, or it won't happen that close to us that it's gonna affect us. I might be wrong. Previously, the brightest GRB actually impacted the ionosphere of the Earth, and it was detected by satellites that wasn't designed to detect. But most of the GRBs, don't worry, it won't happen that close to us. Thank you very much. Yeah. If you have any questions.
So you talk about brightness, but what is brightness? How is it measured? Is it in visible light spectrum only, or total energy, or and then further to that, when you talk about brightness of one object versus another, aren't there a bunch of assumptions made, such as you're sitting in the middle of the jet for extended duration, equal for all objects that you're measuring, and you're not on the periphery of one, or they're not moving, or all that other dynamic stuff that's going on?
That's a very good question. So the question was, what do I mean when I say brightness? And aren't there a lot of different criteria that affect this brightness I'm talking about? So the brightness for GRBs I'm talking about, it is the burst of energy in gamma rays. So like the count of gamma rays we are detecting. So that's the plot you saw there was actually the number of gamma ray detected. So that is very clear, like it was very high, a lot of gamma rays detected. It's not optical. Optically too, it was really bright, but we think that from radio observation and different observation, you already hinted at about the jet. We do think that for this one, the jet was so small, so energy was very, very concentrated in a very small jet. That's why it looked so energetic, as in so bright in the optical light. But in the gamma rays, that is what we are comparing to say it is the brightest of all time, because in radio it wasn't the brightest of all time, in X-ray it was. So it is different, but the gamma ray detection is the brightest of all time.
So brightness is really relevant to your position within the emitted energy spectrum. It doesn't necessarily say that observation A was brighter than total emission or than observation B. It just could be relative to where you were sitting within the emission.
Okay, so if I understood the question, it is about the emission and where we are looking at the emission relative in terms of brightness, right? So I think it's more like energetics. So it was very, very energetic explosion. So we know that it has to be one of the most energetic we have ever detected because of the gamma rays. Now brightness will be affected by different things, like this was also right through, like the universe was kind to have this extreme explosion close to us, but also it was very, very parallel to the galaxy, our galaxy, so it went through all the dust and everything. So all these different things matter with the brightness, but when it comes to energy, it was the most energetic gamma ray burst we have ever detected.
But it's a detection measurement, not necessarily a total emission of what was happening, because it's dependent on where you are positioned, right?
You're right that the jet has to be pointed towards us, so there could be case where the jet wasn't pointed towards us, but out of all the GRBs in our human history that we have detected, this is the brightest.
Right.
Yes.
What are you most excited to learn for the next year?
Sorry.
What are you most excited to learn when the next year may happen?
So just 2 days ago, we detected this GRB, which is around redshift of 6, which is around 11 billion light years away, maybe. I think so. I'm not very sure. Sorry? More. Okay. Yeah. Sorry. Okay. So it happened very recently. So we are very excited to figure out like if the supernova associated with this high redshift GRBs will be different, and what kind of properties it will have, because it will have implication on the stellar evolution and other things. Yes.
These high redshift GRBs, can you observe them with gamma ray satellites, or you need?
Sorry, I didn't understand.
These high redshift GRBs, can you observe them with gamma ray satellites, or do they get redshifted completely?
It was detected by gamma. Like it's always like usually it's Swift or Fermi GVM. Those are the things that detect this gamma ray burst. Looks like we're done. Yeah.
Alrighty, thank you, Anisha. And with that wraps up Space Drafts 95 for us. We will reconvene here at 7:30 p.m. on Tuesday, not Thursday, geez, I know what I'm doing today, on Tuesday, March 19th, right here, same time, same place. Just a couple of reminders. Number one, don't forget to tip your bartenders. Number two, we have a merch table. We've got freebies. For those of you who correctly answered the trivia questions tonight, we have stuff for you over here. We also have eclipse glasses for the eclipse in April. And I think that just about wraps it up. So, see you next month, and thanks for coming.